Welcome to this presentation on anomaly detection, with a focus on leveraging artificial intelligence for fraud detection. This will provide a comprehensive overview of anomaly detection techniques. Anomaly detection is the identification of rare items, events, or patterns that significantly differ from the majority of the data. In other words, it spots things that don't conform to expected behavior. Anomaly detection identifies patterns that deviate from expected normal behavior. It is essential for various applications, including fraud detection, system health monitoring, and security, using statistical methods and machine learning algorithms to pinpoint unusual occurrences. In fraud detection, anomalies can manifest in various forms. We will explore three primary types of anomalies. The first type is point anomalies, which are individual data instances that deviate significantly from the normal pattern. For example, a single transaction with an unusually high amount. The second type is contextual anomalies, which are data instances that are anomalous in a specific context but not otherwise. For example, a normal transaction amount at an unusual time or location. The third type is collective anomalies, which are a collection of related data instances that are anomalous with respect to the entire data set. For example, a pattern of small transactions followed by a large withdrawal. There are two primary approaches to anomaly detection using artificial intelligence. The first one is supervised learning, where a model is trained on labeled data to classify transactions as fraudulent or not fraudulent. Here's an example of how to train a fraud detection model using a random forest classifier from Scikit-learn in Python. The second approach is unsupervised learning, where the model identifies anomalies without labeled data by finding deviations from the norm. Here is an example of using an isolation forest algorithm to detect anomalies in a set of transactions. Deep learning techniques, particularly autoencoders, are effective for anomaly detection. Autoencoders learn to encode and decode normal data, and anomalies are identified based on high reconstruction error. The diagram illustrates the architecture of an autoencoder, consisting of an input layer, encoder hidden layers, a bottleneck latent layer, decoder hidden layers, and an output layer. This is the implementation of an autoencoder model using TensorFlow Keras. The code defines a function to build an autoencoder with dense layers, including an input layer, encoded layer, latent layer, decoded layer, and output layer. This diagram illustrates a typical fraud detection system architecture, showing the flow of data and processes involved. Data sources such as transaction data, user behavior, and historical patterns feed into the data ingestion stage. Next is the processing layer, where feature engineering is performed, followed by real-time and batch processing. The machine learning layer consists of real-time and batch machine learning models, which contribute to an ensemble decision. Finally, the output layer includes an alert system, dashboard, and API endpoints for various actions and insights. Here are some code snippets illustrating key aspects of a fraud detection implementation. First, we have an example of feature engineering, where new features are created from transaction data, such as time-based features, amount statistics, and location features. Second, we have an example of building a model pipeline using Scikit-learn, including steps for scaling, feature selection, and classification using an XGBoost classifier. Real-time fraud detection requires efficient stream processing to analyze transactions as they occur. The processing logic involves extracting features from the transaction, applying a rules engine to evaluate the features, using a machine learning model for prediction, and combining the scores to make a final decision. This flow diagram illustrates the real-time processing pipeline. It starts with a transaction input, followed by feature extraction. Parallel processing occurs with a rules engine and a machine learning model, leading to a decision engine that determines the outcome. To evaluate the performance of a fraud detection system, it's important to use appropriate metrics. Some key performance metrics include precision and recall, which balance accurate fraud detection with minimizing false alarms. the F1 score, which is the harmonic mean of precision and recall, providing a single score for model evaluation. ROC-AUC, which measures the model's ability to distinguish between classes across various thresholds. Finally, average response time, which is the speed of the fraud detection system in real-time scenarios. When implementing a fraud detection system, it's important to follow best practices and consider key aspects. First, in terms of technical implementation, it is important to implement robust data validation and sanitization. Use model versioning and A/B testing. Maintain comprehensive logging and monitoring, and implement fallback mechanisms for system failures. Second, regarding security and compliance, ensure GDPR and data privacy compliance, implement end-to-end data encryption, perform regular security audits and penetration testing, and maintain detailed audit trails for all decisions. Third, in terms of model maintenance, regularly retrain models with new data, monitor for model drift and degradation, implement automated performance alerts, and document all model updates and changes. Finally, regarding performance optimization, optimize the feature engineering pipeline, implement caching strategies, use distributed processing for scalability, and conduct regular performance benchmarking. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.